Have you ever wondered how these heavy and hard-working machines work? It's because of their hydraulic systems. They use pressurized, incompressible fluids, typically oil, to generate all the lifting power it needs to pick up large loads. A loader backhoe uses a piston system called a hydraulic ram. The ram is fed by two hoses on both ends of the actuator, letting the piston move in both directions by applying hydraulic pressure to move its arms. Forklifts use pressurized incompressible fluid to move the forks up and down using hydraulic system. The automotive braking system uses hydraulic brake fluid, typically glycol. The fluid pressure stops the wheels in motion. Your car's steering system uses pressurized hydraulic fluid to change the wheel angle of your front wheels. Its hydraulic system reduces your effort to steer the front wheels into a smooth and quick directional change of the vehicle. The hydraulic fluid also acts as a coolant and lubricate the various parts under the hood. Hydraulic systems are used in airplanes a lot to operate the landing gear, brakes, flaps, and flight controls, to name a few. The reason hydraulic systems are used on airplanes is because they provide a perfect amount of force or pressure without requiring too much fluid on board the aircraft, making them a big advantage to reduce aircraft weight, thus reducing fuel consumption. Hydraulic fluid is not susceptible to compression, which means that as the plane takes off to high altitudes, the fluid pressure is not going to change because of the fluid's incompressible properties. Even a simple trolley jack uses hydraulic system with incompressible oil to lift your car for a tire change or under chassis repair. Now let's look at some definitions of hydraulics. It is the study of how fluids behave when they are in static or dynamic condition. It is a mechanical function that operates through the force of the pressure of the confined, incompressible liquid. Pressure exerted anywhere in a confined fluid is distributed equally in all directions throughout the incompressible fluid. Pressure increases the system capacity. The more pressure, the greater is the system capacity. Force applied at one point is transmitted to any point using an incompressible liquid. It is similar to pneumatic systems in function. Both systems use pressurized fluid power, but hydraulics use liquids, while pneumatic system uses gases. A minimum application of force is only needed to enable the operator to perform a lot of heavy work. An understanding of hydraulics allows cities to keep water supplies and sewer pipes flowing. Hydraulics versus pneumatics. In hydraulics, a liquid or oil is used, while pneumatic systems use compressed gas or air to transmit power. Hydraulic systems work better because the liquids used are incompressible, meaning there is no delay in the movement of the actuator to lift, push, and pull objects. Pneumatic systems have some delay in movement since the gases has to be compressed first before a pressure is generated. Pascal's law applied to hydraulics by Blaise Pascal. Here is the illustration. A force F1 is exerted over the area A1 on cylinder 1, state point 1. The relationship between the two values is pressure is equal to force over area. On the right side, a force of F2 is exerted over the area of cylinder 2, which is A2. The relationship is pressure is equal to F2 over A2. The pressure exerted anywhere in a confined liquid is equal in all directions throughout the incompressible fluid. which means P1 on the left is equal to P2 on the right. The force applied at point 1 is transmitted to point 2 using an incompressible fluid, which means F1 will be less than F2. Pascal's law example. A 1,000 pound force is applied at point 1. Determine the upward force at point 2. So we have F1, 1,000 pounds. The area of the cylinder is 25 inch square. So we get a pressure of 1,000 pounds divided by 25 inch square. We have 40 pounds per square inch. It means there is a 40 pound per square inch of pressure at any point inside the closed system. Over at the right hand side, the area of the cylinder is 50 inch squared with still an unknown force moving upwards. So we get P2 pressure is equal to F2 over A2, which is F2 divided by 50 square inch. Now since P1 is equal to P2, we get P1 is equal to 40 pounds per square inch is equal to F2 divided by 50 square inch. We get F2, 40 pounds per inch squared multiplied by 50 inch squared, we get 2,000 pounds. This will be the weight that can be lifted at cylinder 2. Mr. Pascal said the pressure of 40 pounds per square inch is able to support a load of 2,000 pounds. Multiplication of force or force multiplication in hydraulics. This is the illustration. A force of 1,000 pounds is sitting on top of a cylinder with a diameter of 10 inches. The area is pi over 4 multiplied by the square of the diameter. The area is 78.53 inch squared. The pressure is F1 over A1, which is 1,000 pounds over 78.53 inch squared. We get a pressure of 12.73 pounds per square inch. Over on the other side, the cylinder has a diameter of 30 inches and the force is still unknown. We get the area of pi over 4 multiplied by the square of the diameter equal to 706.86 square inch. The pressure, which is equal to F2 divided by 706.86 inch squared. Since P1 is equal to P2, we substitute the value of P1, which is equal to 12.73 pounds per square inch, equals P2, which is equal to F2 divided by 706.86 inch squared. F2 will now be equal to 8,998.32 pounds, which is approximately 9,000 pounds. So our force going upwards on the right side is now 9,000 pounds. Now we get the relationship between A2 on A1, which is 706.86 square inch divided by 78.53 square inch is equal to 9.0. We can see that A2 is 9 times larger than A1. It means that any force applied at the left-hand piston will appear 9 times greater on the right-hand piston. If you apply a pressure of 12.73 pounds per square inch at point 1, the right-hand piston will be able to carry 9,000 pounds of force. Remember that A2 is 9 times greater than A1. It follows that F2 is also 9 times greater than F1. That is what you call force multiplication in hydraulics. Hydraulic system components. First up is the oil reservoir. It stores hydraulic oil and disperses heat to the surroundings. It also acts as settling tank to allow foreign particles to settle at the bottom. It has baffles to dampen excessive rippling or movement of oil inside the tank. Baffles also allow air bubbles to escape from oil. It allows condensed water to settle at the bottom of the tank since water is heavier than oil. There is a breather on the top of the tank to maintain atmospheric pressure and to avoid creation of vacuum. Tank accessories include a mercury bulb to indicate the oil temperature and a sight glass to determine the oil level inside the tank. The pump is also called a hydraulic pump. It's a vital component in the hydraulic system, responsible for moving the fluid around the system, like the heart in humans. It converts mechanical energy, energy of an object in motion, into hydraulic energy, energy due to movement of fluids. Pump is either rotary or reciprocating. The pump pushes the hydraulic incompressible oil into the lines. The more flow produced by the pump, the greater is the system speed. Next is the directional control valve. This valve allows the oil to flow into different paths in order to achieve a desired movement of the actuator. By flipping a switch, the directional control valve opens or closes ports to redirect oil and its passage in order for the actuator to move in the desired position. Next is the actuator. An actuator is a mechanical device that produces motion, either linear or rotary motion. In our case, the actuator produces linear motion with double acting cylinder, meaning it sucks in oil at the cup end at the bottom and discharges oil on the rod end at the top. Alternately, it sucks oil at the rod end and discharges at the cup end. The pressurized hydraulic oil allows the ram to extend and retract. The actuator is pushed by the oil pressure to produce a mechanical output in order to move the load. Next are the lines going from the directional control valve to the oil reservoir. The pressure relief valve or safety relief valve is a flow control mechanism designed to release pressure above the preset limit. It stops pressure from increasing beyond the preset value. The released oil is diverted back to the reservoir. The relief valve automatically shuts off when the oil pressure drops to acceptable levels. We now have a hydraulic system that's gonna work. But do you think something is missing? Yes. We need a device that ensures a clean, dirt-free oil circulating around the system. We need a filter because impurities in the hydraulic system affect the components and eventually shorten the equipment service life through wear and tear and equipment malfunctioning. Filters are used to remove the smallest insoluble particles and keep the hydraulic system clean. Going back to the directional control valve, this is a three-way valve. On this valve position, pressurized oil is directed to the bottom or cap end of the actuator and exists at the top, rod end. This pushes the piston up to raise the load. Next, on this valve position, fluid is directed to the rod end and exits at the cap end, allowing the load to be lowered. The last of the valve positioning is called neutral. Neutral meaning the hydraulic oil does not go to the actuator but is diverted back to the reservoir. In this case, the actuator is not allowed to move in the neutral position. Sometimes the line from the pump to the actuator experiences high pressure. Once the sensor at the pressure relief valve detects a high line pressure beyond the preset limit, the disc inside the pressure relief valve opens to divert the oil flow through the pressure safety valve to release the pressure. The fluid then flows back to the reservoir. When the line pressure drops to acceptable levels, the relief valve automatically closes and shuts off. I hope you learned something about simplified hydraulic system. Don't forget to subscribe to Engineers Got Talent.